Dr. Nardi here, and in this video we're going to talk about the importance of the neuromembrane, and we're going to discuss why this extraordinarily thin, only about 4 nanometers in thickness, made up of lipids, which are fats, and proteins, is so important to a cell's function. So let's talk a little bit about first what the neuromembrane is made up of. The neuromembrane is made up of lipids, right? They are lipid molecules, and they have a head and a tail end. And the heads of the molecule are water soluble, so they are attracted towards the seawater-like fluid around and inside the cell. The tails are water insoluble, so they're repelled by the fluid. So if you think about this, the heads orient towards the fluid and the tails orient away from the fluid. So the molecules turn their tails towards each other and form a double layer membrane. And this double layer membrane not only holds the cell together, but it also controls the environment around the cell. So some molecules, such as like water and gas, can pass freely through. Other substances are barred from entry and cannot enter the cell or cross the membrane. And still others can have some limited passages through what we call protein channels. Other substances can have limited passage through protein channels. So this selective permeability of a cell contributes to what we call polarization. This means that there's a difference in the electrical charge between the inside and the outside of the cell. Think of this as the difference in charge. I guess you can make a comparison between 2 points, such as like a battery, right? Or between, I don't know, the inside and the outside of a neuron. We call the two charges, right, between poles of a battery, voltage. And that's the same thing we refer to it here, is we refer to this electrical charge as voltage. So if we're going to talk about voltage for a minute, we can actually talk about resting potential. So just like you could hook up your car and get a voltage of your battery, you can also measure a neuron's voltage. And we're interested in the difference in charge between the inside and the outside of the membrane of a neuron at rest, and we call that the resting potential. Now again, the resting potential is just the difference in charge between the inside and the outside of the membrane of a neuron at rest. And normally, and the numbers vary slightly, but you'll see it between -40 and -80 millivolts. And there's a range because different neurons slightly differ. And I would say on average, a neuron's resting potential is around 70 millivolts. So the resting potential is actually due to the unequal distribution of electrical charges between the two sides of the membrane. The charges come from ions, and basically, if you remember your chemistry classes, these are atoms that have lost or gained one or more electrons. And we also have sodium ions and potassium ions. And both of these, by the way, are positively charged. Then we have chloride ions, which are negative. And we also have certain proteins and amino acids that make up the organic anions. So what you need to know is the fluid outside the neuron contains mostly sodium and chloride ions. And the ions inside the neuron are mostly potassium and anions. Something else to keep in mind is the inside of the neuron has much more negative ions than positive ions, whereas the ions on the outside are mostly positive, and this makes the resting potential negative. So there's two forces you need to keep in mind that kind of keep this balance going, which is the force of diffusion. So ions flow from a high to low concentration. If you remember back to your science class, you'll remember that. And also electrostatic pressure. Ions are attracted to the opposite charge, so a positive to a negative, and repelled by the same charge. So a positive to a positive, they'll be repelled. These two forces keep the neuron at balance. Another significant contributor to the polarity of the membrane is the sodium-potassium pump, which I mentioned on the previous slides. And basically what this pump does, it moves sodium ions outside for every 2 potassium ions that move inside. And this helps keep the inside of the membrane more negative than the outside. And by the way, the pump's operation is a metabolic process, which means that it uses more energy. In fact, it actually takes about 40% of the neuron's energy expenditure. Now, before I get into excitatory signals, I want to talk about something. I want to talk about ion channels and local potentials. So we need to kind of get a better understanding of how ion channels work. So ion channels are pores in the membrane formed by proteins, and they gate the flow of ions between the extracellular fluid and the intercellular fluid. And chemically gated channels can be opened by ligands or neurotransmitters, or hormones, by the way, in case you want to know what that word means. And electrically gated channels are opened by a change in electrical potential of the membrane. A neuron is usually stimulated by inputs that arrive on the neuron's dendrites, if you remember that from a previous video, or the cell body from another neuron. And it also could be a sensory receptor as well. So this effect might be excitatory or inhibitory, depending on the ligand and the characteristics of the receptor. An excitatory signal causes a slight partial depolarization, which means that the polarity in a small area of the membrane is shifted towards 0. This partial depolarization distributes the ion balance in the adjacent membrane, so the distribution flows down the dendrites and across the cell membrane. You might think to yourself, is this how a neuron communicates in the rest of, the nervous system? However, what you'll know is a partial depolarization dies out over a distance. It's only effective over very short distances. And for that reason, partial depolarization is also called local potential. And the ion channels in the axon are actually electrically gated, and they have unique physical properties. If a local potential exceeds a threshold from activating these channels, typically, by the way, about 10 millivolts, then more positive than the resting potential, it will initiate an action potential, which we'll talk about here in a few moments. A couple other things I want to note about local potentials. They are graded potentials, meaning they vary in magnitude with stimulus strength. And as I said previously, they do not communicate over long distances very well. They drop off the farther they have to go. And an action potential, as I just noted, follows the all or none law, meaning it'll occur at full strength or it won't happen at all. It's either in or it's out. There's no in between. And by the way, messages travel over a long distance at the same amplitude, so they don't lose strength. So if that neuron reaches a negative 30 millivolt threshold, then it will trigger an action potential. So it's all or none. So once that action potential is reached, the neuron will fire. And an action potential is an abrupt depolarization. And basically, this allows the neuron to communicate over long distances. During an action potential and the initial recovery, the sodium ion channels are open and unresponsive to further stimulation. No matter how intense this time, we refer to this as the absolute refractory period. Now, the importance of this is, well, this delay in responsiveness, I should say, has two important goals here. First, this 1 to 2 millisecond duration of an absolute refractory period limits how fast a neuron can generate a new action potential. And the second part is the ion channels behind the action potential are still recovering, and the impulse can propagate only down the axon towards the dendrites, not back up towards the cell body. And this makes neurotransmission unidirectional, which means it only travels in one direction, towards the tail of the neuron. And at the end of an absolute refractory period, the sodium channels have closed and the neuron is able to fire again. But please note that the potassium channels remain open for an additional 3 to 4 milliseconds as potassium ions continue to exit the neuron. And this polarity is driven slightly more negative than the resting potential. We call it a dip. We call this dip the relative refractory period. Another action potential can be generated, but only from a stronger than threshold stimulus. Thanks for watching, and I'll see you in the next video. Take care. Bye-bye.